think that's just
So I know you used to do it.
I think it's chair.
Terrible system.
Well, it's only, I mean, actually, at one time I did make my mistakes in such a row.
yeah.
Not enough.
Because you can.
Yeah, and ask a question. Let's actually. I don't know, I used to be able to, I wasn't quite sleepy. When I was in high school, we used to pay attention in class. And I had to replay back in order to answer the question.
Something going there while you're dating.
Yeah, just voice record.
Oh, yes. Things stop. Would you see connection panels? Very obscure occasionally.
I could still do something.
Sit up there.
I think that all their issues aside, I think the speed of
Okay, yeah.
I think it's nice after you nudges.
So what do you want?
We'll see, yeah.
We'll have an interesting talk.
You know how things work? You know how much?
I think the mic wasn't earlier.
No, I seem to got lost in my Zoom account. Can you make me host again?
Yeah, I don't know.
We're the opposite ends of the
Very community driver, but for when you think about just rates analysis. So that's referred to AHG, but it's actually honestly this spreadsheet.
So what kind of resolution are you aiming for?
He's gonna latch onto it.
Okay.
Welcome, everybody. This is the CFA colloquium. I'm John Raymond, and I'm glad to be introducing our speaker today, Danny Milisavljevic. Many of you know Danny because he was here for some time. He did an undergraduate degree at McMaster University and went to the London School of Economics to do a master's in philosophy of science, but came back to do regular science at Dartmouth, where he worked with Ron Eason. And then after that, he came here, where he was a postdoc, working with Alicia Soderberg and then Dan Patnaud. And in 2017, he went to Purdue University, where he's on the faculty. He'll be telling us about some exciting results from JWST on the Supernova remnant Cas-A, I think, is the main topic. But a more general topic is Laboratory for Astrophysics. Dan.
Great. John, thanks very much for that introduction, and thank you for the invitation to come speak here. I've had a wonderful time. It's kind of like coming back home. This was such a supportive environment to be in during, a crucial element of my career, and I have great gratitude for all that enabling force that it provided with me. So now I get to come back and share what your child has done. It's like a show and tell. And hopefully by the end of the talk, I'll have convinced you of all the rich science that goes into interpreting what we see here. And this is, as John was mentioning, this is a supernova remnant Cassiopeia A. I'm here, let's see if this, yes, I'm here by myself, but I have to acknowledge my team. These are the students that I work with at Purdue University. We're going with the Barbie theme here. It just so happens I encourage you to look at the paper that my grad student, Bhagya Subrahyan, who's graduating this year, put out this year. Using this system that I'll describe at the conclusion, hopefully there's time for it, we encountered this wild object, which is arguably among the most energetic transients we've ever encountered before. It had the ZTF name 20, ZTF 20 ABRBEIE, which was a mouthful. So one night, Danielle Dickinson looked at it cockeyed and she said, Barbie. So that's how it got the name Barbie. And then scary Barbie, because when you look at the energetics, all of a sudden we see this rise of 5 magnitudes up peaking at minus 26 with a total radiated energy of like 10 to the 53 ergs. We'll get to that maybe if we have time at the end. But anyway, so I work with a great team at Purdue. I've been very happy there. And here we go. So here's an outline of what I'm planning to touch on. It's a lot to handle in 50 minutes. I'll begin with a very glossy but important overview of the importance of supernova explosions and a very kind of Reader's Digest version of what's involved with understanding the progenitor star and explosion mechanism. And that will motivate what I'll be presenting, and this is the work that I've been doing. That involves doing three-dimensional reconstructions of supernova remnants. I'll only have time to highlight Cas A, but what I'm showing you here can be applied to a variety of young remnants. And then, yes, the highlight will be all the new science made possible by the James Webb Space Telescope. Again, using Cas A as an example, but try to motivate what we're gaining insight from this one object can be extended to a variety of other objects. And then some fun stuff. You'll hear me say this a lot. I spend time with supernova remnants because they're resolved, at least the ones in our own galaxy. Okay? So I can actually see what's going on. The rest of the time, I'm chasing dots, the unresolved supernovae and extragalactic supernova, and extragalactic systems. And there's a lot of interesting science possibilities that can be made possible to the Rubin Observatory. And I will touch on this a little bit because everybody's excited about possibilities with multimessenger astronomy. I'm co-PI of the Supernova Early Warning System, which is a network of neutrino facilities, and so I'll talk about some motivation with that. Okay, this is an image that will be familiar for a number of people. It's a field in the Large Magellanic Cloud. The arrow is pointing at a star that should not be seen as remarkable because you see other stars of comparable brightness, you see brighter stars, but of course the arrow points at something important. This is Sanduliac minus 69202 because what happened? Well, of course, I'm going to learn this in a moment. There we go. In 1987, in February, okay, that star exploded. And this is important. This is the naming convention, the year, and then, this increases A, B, C, D by the number of objects. This was in February. That was the first supernova, okay? Now we're up to sequences of like 5 and more letters because we're finding so many in any given year, tens of thousands. It's also appropriate that it was co-discovered by a Canadian, 1987, eh? I'm from Canada, so I get to use that joke, as terrible as it is, okay? Going further, we can follow the continued evolution of that sequence. So, for instance, looking at it with the razor-sharp vision of Hubble Space Telescope, we see that as Bob Kirshner would say, we do a nose count and we don't see that star anymore. I could spend the whole lecture dissecting what we see here. This ring and this ring is not ejected. That's associated with mass loss from the star before the explosion, as is this ring. Okay, the exploded debris is this stuff right here, and we can continue to watch it over years. And I mean, it's amazing to watch what's happening. So this is an initial position where the shock wave is beginning to interact with that circumstellar disk. And this is thought to be left behind by a binary system that merged about 10 to 20,000 years prior to the explosion. And then as time progresses, you see more and more of that circumstellar disk getting heated. And for me, even more important and even more bizarre is you see the evolution of the ejecta. Okay? This is no spherical cow of gas. Okay? It has real asymmetry associated with it. A lot of key things about this one object to remember as we go through. One is that image that I showed originally, okay, of the progenitor star. Until this time, it was naturally thought that the progenitor system for a type 2, so a hydrogen-rich explosion, would be a red supergiant. But what do you know? It's a blue supergiant. Okay? Now, theorists retroactively predicted that blue supergiants could explode following this discovery, okay? But it was our first realization that we didn't have the whole story, okay? There was still more to tell. And then the other thing is that you see here, as I was pointing out, it's asymmetric, okay? So these explosions are inherently asymmetric, and we have to push into 3D to really understand what things are going on. And because I showed 87A, I included this slide last night because of new results that came out. This is a new issue. Now, take this with not with a grain of salt, but with the understanding that if you've been following this field, there's a claimed detection of the surviving neutron star, every 6 months, okay? And this is the latest one. But I find that this one will really hold weight. Okay, so you see here it is like this is plain simple. So the explosion's in the center and we see a dot in the center. For many years, there's been keen interest in identifying the collapsed remnant that's left behind, okay, the surviving neutron star. In this case, they seem to have identified it as a pulsar wind nebula, or at least in the sense that this hot light bulb is illuminating supernovae ejecta around it, in this case seen in the argon lines. Anyway, another reminder of the importance of this event, it truly is our first multi-messenger source outside of the solar system. Okay? There were about 20 neutrinos that were detected from 87A. Given the modern era, we anticipate that we should be able to detect thousands of neutrinos from the next galactic supernova. A lot of opportunities for rich science. Okay, so this is a crowd that's somewhat informed, but let's remind ourselves about all the things that motivate trying to understand supernovae, because they so broadly impact astrophysics. Among other things, they're drivers of cosmic evolution. They help galaxies evolve. They provide it an energy budget. They shape its structure and provide metal enhancement. From stellar death, they can actually trigger star formation. Supernovae are a significant source of dust, which are the building blocks of new star systems and planets. They produce a variety of exotic objects that many people like to study: neutron stars, black holes, and some gamma ray bursts. As I mentioned, they're prodigious emitters of neutrinos. They are progenitors of gravitational wave systems, so the neutron-neutron star mergers, the black hole mergers, okay, those all came from supernova. And supernovae produce gravitational waves themselves. We'll discuss that a little bit. And, the oxygen we breathe, the nitrogen in our DNA, supernovae manufacture heavy elements that make life possible. There are many questions that one may ask behind supernovae, and this is why I put it as a title, an extreme astrophysical laboratory. There's so many experiments that you can run. The ones that will drive the discussion today will be what types of stars that explode. Okay? I already told you the rude awakening that 87A provided. Since that time, we've actually found, for instance, that yellow supergiants can explode as well. Okay? Next, how do stars explode? What is the explosion mechanism, that complex, beautiful magic that happens at the core of the star, where you have the implosion and then the explosion? When I started my PhD, oh gosh, we're going back 20 years, I was focused on this question. I thought this was stamp collecting. Okay? But in fact, the last 10 years have really demonstrated us that if we're going to understand how stars explode, We truly need to understand the type of star that explosion is taking place. Okay? And not just the type, but the whole progenitor structure that that explosion is moving into. Okay? That can really influence the type of explosion and the output. So again, just to do a glossy overview, the star begins as the massive star of about 8 to 10 solar masses, begins as mostly hydrogen, some helium, and trace amounts of trace amounts of other elements. It goes through successive stages of fusion. It reaches iron core fusion. That process is no longer exothermic. The core is robbed of the radiative pressure it needs to support itself. Electron degeneracy pressure helps you out for a little bit, but ultimately that even collapses. It comes down. There's photodisintegration. There's electron capture. You produce a lot of neutrons. The neutrons say, hey, we don't want to get too close. The strong force kicks in. There's some magic that happens. There's a little bit of a rebound. Okay? These are the details that people are trying to understand. But anyway, it reaches a point at which the collapse halts, and there's a shock wave thought to be sent out and disrupt the star. The problem is that decades of simulations were not successful in being able to make this explosion take place. They would just continue to collapse. Now, in this day, we know that black holes exist, so it truly is the case that in some cases they will collapse down. But we also know that supernovae explode, okay? So they can't all collapse. There's some other ingredient that we need to add. These days, I think if you ask most people, they would agree that neutrinos are kind of the key element that drive these supernova explosions. Now, normally, the neutrinos that are formed in the processes that I mentioned will stream through unimpeded, but at these intense densities and temperatures near the core, there's enough cross-section where they can impede energy into that inner layers and help hopefully revive the shock. Okay? That heating is going to be uneven. And so in addition to neutrinos, it seems to be that the breaking of spherical symmetry is essential for the core collapse process. Okay. On that topic of breaking spherical symmetry, I had a whole set of slides that I had to remove at the last minute because I didn't want to be too rushed. But another thing that we've come to appreciate over the last 10 years is that stars seem to be preluding their demise as a supernova with some kind of precursor outburst. Okay? Which is to say, if we monitor some systems, it looks as though they have these massive mass loss outbursts preluding the core collapse. And the timing, months to years before the supernova explosion leads us to think there must be information being transmitted from the core to the envelope. And when I was a grad student, I was told that's impossible. The scales are too large. And yet we still have that scenario. For that to happen, we have to cross out this Wikipedia slide, okay, and adapt something like this. So maybe this is good for a lot of main sequence burning and these stages of stellar fusion. But as we approach the final phases, perhaps around carbon, but most definitely around neon and silicon burning, we have these turbulent flows that it's set up as you're changing between nuclear fuels. And then you have to imagine that this is what the explosion is taking place into. We have a seed explosion that's running into this perturbed interior, such that what would originally have been a failed explosion, if it were exploding into a spherically symmetric distribution, if you have a perturbed interior, it can have a successful output. Okay? So that's the problem. Okay? I want to be able to understand what's happening at the core of the star as it's exploding, to understand the magic of the core collapse mechanism. So how do you do that? The common game is strength in numbers. You look at the copious number of extragalactic supernovae in the universe. What's the commonly cited rate? How many supernovae are going off in the universe at any given time? Depends on who you talk to, but generally once a second, apparently. Okay? And yes, many of those are too distant for us to be able to observe, but current facilities have the ability to discover upwards of tens of thousands of supernovae in a given year. So you have strength in numbers, so many. But the problem? They're dots. Okay? They're dots. So, and don't be distracted by beautiful host galaxies. Okay? They're just dots. Okay? Now, astronomers, historically, we're really good with dots. We can image in different filters across, the electromagnetic spectrum. We can take spectra. We can do polarimetry. There's a lot, but it's a dot. And if you want to get out the three-dimensional properties of the explosion, there's inherent ambiguities. You're always going to be faced with. You're always going to be faced with. Okay? So, why not take a different approach? Instead of the many and distant, we do a few up close. So what I'm showing here are examples of galactic and SMC, LMC remnants. If we get the debris fields of these massive star explosions within a couple thousand years after explosion, if you wait too long, there's too much interaction with the surrounding environment that perturbs the structure. But as it happens, so much of the dynamics of the explosion is frozen in within a few weeks after the original core collapse, and then you just have mostly, he says, a homologous expansion beyond that. Okay? There can be deceleration, but if you work in the certain wavelengths, you can really minimize the amount of deceleration and get a sense of the geometry of the explosion. So today I'm focusing on this object, Cassiopeia A. And for more history, why is it called Cassiopeia A? Radio source, right. So Grote Reber discovered this as a radio source using his home radio telescope. There's a great story. At 26 years old, he built this enormous, how many meters? 12-meter radio dish in his mom's backyard that he was living with. And he published this report on Cass A. So it was originally identified in the radio, and then Rudolf Minkowski and Walter Baade found the optical counterpart to it. We write 1680 approximately here because there's no credible historical sighting of when the actual supernova took place. But there are ways that we can estimate of when that happened. Okay? Why am I highlighting on Cass A? There's a number of things. Here's a list of them. One, it's the youngest example that we have of a core collapse explosion occurring in the Milky Way. It's fairly nearby. It's the only supernova remnant with a secure spectroscopic classification, which is important. So that means because nobody was around in the 1600s to be able to take a spectrum and to be able to compare it to the modern day nomenclature for supernovae, we can actually benefit from the fact that light is finite in velocity and it goes in all directions. So even though the light did a direct line towards us and arrived somewhere around 1680, it went backwards and then reflected off dust clouds and came back to us, and people took spectra of that and was able to make the classification. And it's among the best case studies for formation, destruction of dust and molecules. Let me take a moment to highlight this. In extragalactic studies, there's many from which supernovae have been discovered to have dust production associated with it, which is exciting, okay? Because we need to know early universe galaxies seem to have much more dust than you would think they would. What's the mechanism that provides it? But an important caveat to dust production is dust destruction. Okay? How much actually survive afterwards? And supernova remnants are one of the only ways that we can investigate that, and Cass A is a great case study. There's an important yet enigmatic neutron star. So it's a very young collapsed object. And unlike the Crab Nebula, which has this strong pulsar wind nebula, so strong magnetic field, accelerating charges around it, the source in Cass A is inert. And that's kind of puzzling. There's various reasons why that may be that I don't get to go to. If you want, you can ask about it. And yeah, it's been observed across wavelengths, especially with all major NASA facilities, so it was a no-brainer to want to pursue this with James Webb. Another just kind of key point that I really need to drive home, okay? Maybe this is a reaction from getting rejected JWST proposals back, okay? Why study one object, okay? Because if you're going to have any confidence in interpreting data from the distant universe in this high redshift galaxies, those are blobs, and then you're doing clever things with the photometry and spectroscopy trying to model it. There's a lot of assumptions that go through every step to go from images or spectra to an estimate of the stellar mass, of the star formation rate, right? All that is dependent on assumptions that are informed by calibration sources like CAS-A. Okay? So the total ejecta mass that will be distributed, the nucleosynthesis yields, the total dust, we need information from this from which we can know. If we can't figure out what's happening with CAS-A, we can't have any chance of what's happening at the distant universe. That also goes to early explosions. Okay? The physics may be a little bit, well, the physics will maintain. The situations may be different. So the stars will be a little bit more massive, less metallicity. But again, there's concepts that will naturally translate from a study of this object to that. Okay, I'm going to get off my soapbox and keep moving on. So here is 50 years of observations of Cassiopeia, dating back to when they were first observed with Abada in the Palomar 5-meter telescope. So you can see a couple of cool things. So let's see if I can watch this with you. So it's an explosion, right? And everything started around here. And how do I know that? Because I can follow the expansion and trace out the vectors and then trace them back. And this is how we know where the explosion center is and around the time of explosion. Here's a different multi-wavelength look of CAS-A. This is going to provide an anatomy that'll set up what we're going to see in the upcoming slides. At the periphery, so in Chandra at around 6 eV, okay, this is highlighting where we have the forward shock. That's the original blast wave that started at the core of the star that moved its way out through the envelope and then into the surrounding CSM-ISM. And then what that does is send a reverse shock propagating in the Lagrangian sense backward that's illuminating what we see as this bright main shell ring. Okay? That's going to come up. Here is the central compact object that I talked about that we only see in X-ray, and I'll get to the trailer here is that we didn't detect it in Webb as would have been potentially consistent with the fallback debris disk, but more on that later. So here is the anatomy. What we were interested, let's go on. So we have the forward shock, we have the main shell. Okay, that sets up the anatomy for what we're going to discuss later on. And then, an incredible aspect, it has these outflows. So while this is moving at around 5,000 kilometers per second, there are outflows. Some people call it jets, but theorists balk at that because it's not highly collimated. But material that's moving upwards of 3 times the velocity in this direction, southwest. So if you look at it in the right wavelength, so for here we see Chandra emphasizing the silicon emission. We can see this kind of northeast-southwest outflow. I highlight this because it's a scenario where at extragalactic distances, we would not necessarily be sensitive to this. It's in the plane of the sky. It's not pointed towards us. It has energies about 10 to the 50, which is 10 times less than the kinetic energy of the overall explosion. So normally, we would not be sensitive to this. But thankfully, because it's right up nearby, we're able to see this. And let me just share this with you. So these are 2 epochs of HST images in the infrared, and we're blinking back and forth. So here, and then we go in the northeast jet. I'm going to enlarge even more. Okay. Kind of remarkable. So these are bits of stellar debris. They are sulfur, silicon, calcium enriched. You don't know what's a star and what's a debris knot until you go through the multiple epochs. And here you can see them popping in. I was talking with John here. It's remarkable how localized they can just pop in because of running into inhomogeneities in the surrounding environment. Okay, so 3D reconstruction of Cas A. What can we learn? One is that there is large-scale coherent structure that's imprinted into the stellar debris. So here we're looking at the rear. You see this large ring here. This is a Mercator projection of what I'm showing here. Okay? So encoded in this morphology is insight into the explosion dynamics. Basically, I talked about uneven neutrino heating. That can encourage the mixing of radioactive elements like nickel-56 to go out ahead of the lighter elements. And then all of a sudden that radioactive decay, nickel-56 becomes cobalt-56, becomes iron-56, and that carves out cavities in the stellar interior. Okay. And then what's interesting is it's not uniform. We have one dominant cavity, and then we have upwards of 5 or 6 smaller cavities as well. Okay. They show up as rings in the reverse shock shell because that reverse shock is propagating as a spherical shell inwards, and it's only sampling, that shell of what's otherwise a bubble-like distribution of these cavities inside. Okay. Now, one of the cool things, so by the way, this is a comparison between observations and simulations. This is showing Chandra mapping of iron-rich ejecta, which would have been originally nickel-56. And you can see, in case, you can't see it so much there, but it's obvious here where that large ring is, we have a large deposit of iron. That's consistent. Now, what's unusual, and by the way, this is seconds after explosion, and this is hours. So the idea is, hey, we've got these nickel-rich plumes that are moving out ahead of the lighter elements, forming these nickel bubbles. The problem is, this is going to motivate the Webb observations, the problem is that nickel-rich material in the simulations is only moving of a few thousand kilometers per second. Okay, here, this is a plot showing the velocity, and this is the amount of material at that velocity. I've highlighted the nickel in these two simulations. You can see that conservation of momentum, most of the heavy stuff, sticks at slower velocities. Okay? The iron-rich ejecta in Cas A that I just showed you, okay, is out here. Much higher velocity. So, if I interpret this naively, I would say, oh my goodness, because that's a log plot, there's orders of more magnitude iron-rich material in the core. That's not going to happen. Okay? So what's actually happening is there's much more mixing than is being accounted for by these models. And in fact, this motivated people to go back to the drawing board and change the progenitor structure. What I'm showing you here is for a type 2 explosion with a massive hydrogen envelope. If you strip that hydrogen envelope back, as is done here, here's thousands of kilometers per second, and you can see a much more flat top distribution reaching out to, now we're overshooting, upwards of 10,000 kilometers per second. Okay. So, for us to truly understand how that explosion proceeds, we need to know how much iron is inside this shocked region. The Chandra data that I showed you, that's the result of reverse shocked iron. And there seems to be 1/10 of a solar mass there. Okay? Now, a typical type 2b should make no more than 1/10 of a solar mass. So all of a sudden it becomes vital and important to know, is there another 1/10 of a solar mass inside? Is there, 100th of a solar mass? Okay. How do we get at that? We have to get at the unshocked ejecta, which is very cool. Not hip cool, temperature cool, of around 100 Kelvin. Okay. And that's the range of infrared that Webb is sensitive to. So, okay, we have the James Webb Space Telescope. I'm sure you've all been hearing lots about it. Our Cycle 1 program was awarded 45 hours. We got an additional 7 hours because the original tiling of the mosaic failed, so we had to fill in the gaps. And there were a number of scientific objectives, hence why the survey was designed to be, hence why the survey is so large, because it was designed to encompass so many scientific objectives. The one that I'm going to highlight here is that ability to map the unshocked ejecta. So the material that's closest to where that core collapse explosion took place. The observation's made up of various imaging mosaics with NIRCam and MIRI, and there's a number of IFU spectroscopy as well. Oh, this is just showing the excitement. This is, by the way, what I'm showing you is 7 years of anticipation as far as designing the survey, getting it approved, waiting after delays, and things finally working. Here's the paper that just came out. All right, what was the payoff? So here I'm showing what our best access at around 24 microns with Spitzer was before James Webb, and this is now with James Webb. Okay? And again, it's one of those things, in hindsight, I can kind of see some stuff here, and there's a little bit, here, right? But only with the sensitivity and resolution afforded by a 6.5 meter, $10 billion telescope can you really start to make out stuff. Okay? Here is the composite image using a subset of our filters. Again, here is the main shell. Okay, that's also bright in X-ray. You saw it in the optical. Okay. One of the surprising things was how bright the circumstellar material was surrounding Cassia. So this is gas that had been released by the star before the explosion. And the forward shock wave that traced, I could follow the outline here, is run over this material, and it's heated it, and it's now emitting in the infrared. Okay? So we have information about the mass loss environment of the progenitor system. In the center is something that came to be called the green monster, and it took a good year for us to settle on the nature of that. I originally thought that that was the unshocked ejecta that I was talking about, because it was so plain face, right? But analysis that involved the spectroscopy of our survey, but perhaps most vital, contributions from Chandra in the location, has actually identified this to be associated with circumstellar material that's towards us. So if here's the explosion, it's the foreground. Now it has a lot of curiosities in itself, but it actually ended up being photobombing our attempt at understanding the unshocked ejecta, which is much more faint here. Okay? And it's behind this, and I'll show you our ability to remove that afterwards. Okay, and now we're going to the NIRCam image, shorter wavelengths. Recall, this is cool gas emitting in the infrared, so we miss out on the interior unshocked ejecta, but what we gain is resolution. We also gain a larger field of view. So what was originally the dusty circumstellar material, it's still there, but at the near-infrared wavelengths, it's now dominated by synchrotron radiation. You see that white, ghostly emission surrounding it. So this is in the periphery. This would be projected in front and potentially in the back. The light echo. I'm going to plant a question if you want to ask me about it. This was a real unexpected surprise. We gave a lot of tolerance in the roll angle of the spacecraft, and we very easily could have missed this, but it has this, what I talked about before, being able to take spectroscopy of the original light from the supernova. Here's a similar scenario, but it was resolved in a way that we'd never been able to before because we never had James Webb before. I can discuss that afterwards, but I got to press on. The thing that you really value from these observations is the incredible detail. So not only are we able to localize ejecta in terms of the elemental abundances, but we can actually see processes of the shock running over material, stripping it, ablation trails, condensation of dust and molecules before in the trailing material. It really is incredible. Okay. So I refer you to Figure 3. It's a nice storyboard of the various discoveries. I'm just going to touch on what I already said here about the green monster emission. If I highlight here, you can see these beautiful, mysterious rings. And when I originally looked at this and thought it was the unshocked ejecta, I thought there was fragmented nickel-rich material that had carved out these bubbles. But as I said, it really is confirmed for us that this is circumstellar material. And there's a working hypothesis that if you have a gas, okay, the dusty circumstellar material of the progenitor star that was released maybe 10 to 100,000 years ago, but then you have the shrapnel of the supernova ejecta. I showed that slide in the northeast jet, you know, the gunshot. Imagine that now being fired through that gas, and the forming holes that have been carved out from that. Okay, so I mentioned already the important clue was the correlation with Chandra. I'm going to have to move on, but there are important locations where the emission from the green monster correlated with the Chandra X-ray. So this really gave us a sense that this is associated with forward-shocked material. And it actually was helpful for interpreting Chandra because there had been a lot of discussion, continues, as far as the crinkly stuff, the blue crinkly stuff in Chandra is that forward or reverse shock material. And here we're able to localize it through a joint venture with Webb and Chandra. Okay, I'm going to move on. Okay. Of all the things I'm talking about, I hope this image stays in your mind the most. Okay? I told you how this is kind of photobombing. All of a sudden, this isn't the inner ejecta that I wanted. It's stuff on the periphery. Still cool, but not the main event, as it were. So here I'm showing the longest wavelength image at around 25 microns, really burned in, as it were, to show where there's emission. And it's a mess, right? You've got shocked, unshocked, ejecta, circumstellar material, all these things contributing. There's projection effects, okay? But through some clever subtraction of filters and some gauging, some masking, we can work some astrophysical magic. Okay, so what I did here is just inverse. So from black becomes white, inverted, and then a little bit of filter subtraction. You can ask me about the details, some masking. This is the treasure map that we had sought after. Okay? In black has been masked all the shock material, so don't be distracted by that. Okay? So we don't have access to that, but what we do have access to is all the gas that has not been shocked. Okay? As a reminder, this bright main shell, okay, it's emitting strongly in UV and X-ray photons, and those shine inside, illuminating this gas that has not yet reached the reverse shock. And all of a sudden, we have this knowledge of a web-like network of unshocked ejecta. Okay? I'd shown a previous slide of a three-dimensional reconstruction where from the ground we were able to map out some of the near-infrared lines where I got a sense of the cavity-filled interior. But this goes an order of magnitude beyond that. So I'm no longer limited to the brightest emission, and now I can see just how extensive the network of unshocked ejectas. This is oxygen ejecta, and our team is now working on doing other elements as well. Okay? When you compare this now to other wavelengths, so from Chandra, we have knowledge of where the X-ray ejecta are, which was original nickel-56. And from NuSTAR, we have knowledge of where titanium-44 is. Okay? These are the radioactive elements that would have shaped the explosion, in addition to that uneven neutrino heating that would have pushed things in certain ways. Now, we have a true test for any core collapse simulation. You know, this is what you should get as an output. It's arguably one of the strongest tests that any simulation will be able to do. And we're not just talking recreating the observables as far as electromagnetic radiation, but multimessenger as well. Okay? Incorporating the asymmetries and the distribution of the elements. Oh, okay. So here is, yeah, me and there was a whole sequence of slides here talking about the fun of the last year. So I was on 60 Minutes. Many people probably don't know this. I see a lot of young faces. 60 Minutes, if you don't know, is like news for old people by old people. But, you know, it's kind of cool. I've been watching it for many years, and I was on there, and I don't have time to show the film. We got noted by the White House. So Jill Biden was doing advent calendar, and she wanted something cosmic inspired. So this really took off. It got in the New York Times. Can you imagine my surprise sitting to eat dinner, watching CBS Evening News and Norah O'Donnell showcasing it, and then the next morning, Savannah Guthrie talking about Cassie, and then the National Space Council in the background. There's Kamala Harris in the center there. There's the remnant. And I'll tell you, for anybody who has a favorite object, this really kills you when they tilt it in some funny way, you know? Think of your loved one. Somebody makes a portrait and they hang it sideways, okay? But it was there. And then, yeah, people who do these things, the Space Telescope likes to send you these numbers. So apparently it was seen by 3.1 billion people. And this one, 3.8 billion people. Purdue likes these numbers too. They say 8 billion people. There's 8 billion people in the world. I don't think everybody saw it, but anyway, they always cover it, where is it? Potential readership. So that's a key word there. Okay, I'm going to take 10 minutes. Is that cool? Okay, the last 10 minutes, I've been talking about the benefits and the importance of working on resolved observations of supernova remnants. Now I'm going to talk about chasing dots, because that is an important complementary study, because we only have a handful of objects for which we can do the types of analysis that I'm showing you. And certainly, given all the diversity of progenitor systems, especially in binary systems, different mass ratios, different orbital separations, metallicity, there's a lot of parameter space to explore. So I've been talking about a lot of these things that you get from supernova remnants. Now let's talk about some of the others, including light curves and the MMA that everybody's so excited for. Now, why? Well, I talked about trying to get out what's happening near the core. And truly, the only way you can really know what's happening at the core, I mean, I can't even send a grad student out to some distant massive star and wait for it to happen, because they'll get burned up. The only way to know what's happening at the core is getting live information that's transmitted by gravitational waves and neutrinos. And here I'm highlighting some of the sciences that you get. Okay? With gravitational waves, well, actually, let me go to this. I dug this up for today's talk. So in 2017, I organized this seminar series on gravitational wave astrophysics, and the first speaker was Ray Weiss. He was so awesome. And this time frame, by the way, it was after the merging black hole system, but it was before the award of the Nobel Prize. And so I remember watching when they called him up at 5 in the morning to let him know that he got the Nobel Prize. And they asked him, Ray, what are you most excited about next? What was his answer? What was his answer? It wasn't more merging black hole systems. It wasn't even kilonovae, merging neutron star system. It was supernovae. He said supernovae. Yes, and I'm glad we can remind everybody about this. The thing is with supernovae, I mean, it's a good and bad thing. It's truly uncharted territory. We don't have any observations to know the signature. And so it's an exciting but scary field, because you're kind of working in the dark. You don't have any real constraints to be able to work from. So that's why he was excited about detecting gravitational waves, because it would be our first hold on that science. So just with a couple slides here, I just remind people that there is this system called the Supernova Early Warning System. I'm one of the co-PIs of this. I lead the multi-messenger follow-up campaign. So the next core collapse supernova in the galaxy is going to produce all this. And the neutrinos will arrive minutes to hours, and I just learned could be even longer, before the optical post-collapse outburst. So here in terms of log scale, we have the the collapse of the core, and then we have the strong optical opacities. It's just going to take time for that shock to propagate and for the, the gamma rays to make their way out before we actually get shock breakout emission in the X-ray and UV. So SNOOS is set up as a network of neutrino facilities that now is going to attempt eventually to triangulate the system. So if one system has a low threshold detection, is not as significant as multiple facilities having some low significant system. And then if it's a bright enough event, then there's the opportunity to be able to triangulate between the facilities and give some localization. And the latest version of SNOOS has various phases. One is just sending out the alert immediately. That should happen within seconds of core collapse. The next thing is localization. Hopefully that happens within a few minutes. And then a few minutes after that, hopefully there's another alert that actually has real-time characterization of the source. So the neutrino light curve will have been long done, and there'll be attempts at modeling that to give a sense of the mass of the star and maybe a little bit more information about what kind of star to be looking at. So our group has been doing many things, most recently coming up with a catalog of candidate red supergiants that could explode. So just like the gravitational wave community, they have a localization, which is very large, but you don't necessarily go after everything. You have priors of galaxies. In this case, we have priors of the galactic plane and stars. Okay, and finally, just to touch on this, because it's a significant amount of my research, but I just didn't have time to touch on it all today. Many people here are aware that we're inching closer to Rubin Observatory. What's the latest estimate? Hopefully by the end of next year, maybe, first light, we'll see, right? So there's the anticipation that we're going to have this enormous increase in the number of supernovae. So I made this a couple years ago, but it's still relevant enough. If you look at all the supernovae that have ever been discovered, we're around 100,000. The first year of LSST operations, depending on what numbers you believe, is going to be comparable to that, or even surpass it. Okay? And yeah, this is the way it works, but you know that. And we're entering this kind of, if this is where we were, this is where we're going to be. Okay? And there's a lot of effort led by amazing people here to try and think about how do we handle this influx? What kind of filters do we need? How do we extract the most interesting objects? What is the most interesting object, right? Some anomaly phase space, etc. So our group is actually trying to do something complementary to that. So instead of emphasizing the anomalous nature of events, if you do have 100,000 supernovae that are discovered by LSST, the majority of them are going to be crummy, like really awful light curves. Maybe you can get a classification out of it. What if, as the survey is progressing, you make intelligent, automated, real-time inferencing of which explosions offer the most science? Or let's say they probe phase spaces that are poorly occupied with current data. So for instance, particularly low energetic events, ones with high nickel yield or very low nickel yield, the extremes, right? Here's an example of what an LSST light curve is going to look like in the first 30 days. It's really sparse. And our team is trying to think about clever ways of being able to anticipate the type of explosion that's happening here, how it's going to evolve, make forecasts about the explosion parameters, and then automate the decision about which facilities are most necessary to be able to fill in key epochs and provide spectroscopy or any additional multi-wavelength data. So our buzz thing is the recommender engine for intelligent transient tracking. Let me just flash this. And Bhagya, who came a couple months ago, would have shown this plot, so it's worth showing again. So you see here, this is now applied to ZTF, which is about 10% the scale of Rubin, so it's a good test. It also has more cadence, but it just changes the problem, but the similar things. As the event is evolving, we have grids of simulations that it's being tested against, and we have estimates of, for instance, the mass loss rate, the nickel yield, the energy, and the zero-age main sequence mass. So in real time, we can get a sense of, oh, is this particularly energetic or not energetic? And we can start making decisions beyond, oh, this is a type 2b, and this is a 1b like 2008D. We can actually get these physical characteristics that would further guide the decision-making with follow-up. Okay, to end, I want to show again this already breathtaking image of Cassiopeia A taken by the Hubble Space Telescope. Okay. I tell you, if you try to image this from the ground, it's hard. It's not particularly bright. This is what it looks like with James Webb. Okay. Optical versus James Webb. And I hope I've been able to tell the story of all the rich science that James Webb is able to provide to us with regard to understanding the progenitor system. So, why is the mass loss like that? What's happening down here? Are they connected? Because the chemical properties seem to think so. Is this connected to what we think was a binary star that merged potentially some time ago? And then all the rich stuff happening underneath here, the unshocked ejecta, where we now have a treasure map of the explosion dynamics of the star, encoded some weeks after the explosion, but not too difficult to be able to trace that back to the first second after explosion. All right, I'm going to flash my little conclusions up there, and thank you for your time.
Thanks, Dan. That was a lot of really exciting stuff. Are there any questions? Let me start. Oh.
In your image that had all the holes in it,
Yes.
some of the holes had blue dots in the center of them.
No, I don't believe you. I don't believe you. So if you're getting at what I think you're getting at, one of the first things that Rob Feason thought was that those could be stars embedded and their winds were carving out holes. I don't know if that's what you're thinking, but that was one of the initial things. So you may have caught one scenario, but that's not the case. Am I answering your question, or do you still see them up there and I don't?
I don't think it was this picture.
The one with the zoom in on the holes, right?
Yeah.
It's a zoom in on the holes.
Oh, okay, like this one.
Yeah. Oh, it's got.
Maybe there. You've got a good eye. That's right. I'm going to go back and look at. Oh, well, hold on. Oh, hold on. You guys should know this. Exactly. Yes. That's PSF. That's art. Yeah. Oh, good. Okay. Okay. That's right. That's an artifact of the PSF and just the image manipulation. The combination of the two will give that. Thank you very much.
Great talk. So you have this amazing Cassiopeia story, all this great detail and stuff like that. What if you do a horrible thing and convolve all that information to a single point? Can you get more information about these high redshift supernovae? Are we getting more insight because we have this amazing picture?
I've done that experiment before. Part of my PhD thesis was when I did that three-dimensional reconstruction of Cassiopeia that I showed, I integrated all the spectra to reproduce what it would look like as an extragalactic source, an unresolved source. Why would you do that? Because then I could do exactly as you said, compare it to extragalactic supernovae. And it happens to be the case that they use this as a benchmark to compare against other events as well. Yeah. So that experiment is a good one. It connects very nicely with one of the best nearby extragalactic examples, a supernova called 1993J. So it was also a type 2b explosion. What does that mean? The star was largely stripped of its hydrogen envelope, but there was still a bit of a hydrogen atmosphere. And we can take spectra of it now, decades afterwards, and we can then compare it to the Cas-A spectrum, which is hundreds of years. And now you have a way to connect of what the evolution is going to be. We have spectra at the time of explosion, we have it hundreds of years and decades, and now we can make connections between the two.
So I'm curious about what you've been able to find out about this, the unshocked ejecta. I mean, its temperature and such things. Ionization state.
Okay, so that is all works in progress, okay? So I'll defer you, you're probably already aware, Martin Lamming, Thea Temim came up with their paper. So all of our analysis is basically, from this data, is consistent in the sense of the densities and temperatures inferred, around 100 Kelvin, etc. What we need to do more work on is between the two IFUs that sample the inner ejecta and give you kind of a column density of what's happening, compare that to the images. That'll give you a little bit more of the filling factor. And those are the kinds of work that I'm doing right now.
I hope this isn't a dumb question, but is there a reason to explore one of the conjectured 1A remnants in the galaxy with this kind of depth of study with space and ground-based
Yes. Work? Yes. By the way, hold on. I got to be polite about this. Let me phrase this. The world is a better place because somebody at Space Telescope flagged my proposal on a 1A remnant for wrong font size. So it was rejected without consideration. So never deviate from 10 point, everybody. Anyway, yes, the obvious one, which I obviously am, not related to, but I am, the Kepler supernova remnant. There's a case where the 1A is interacted with surrounding. It's the obvious one because it's bright and infrared. Okay, there's a lot of other exciting things to potentially do there. I didn't get into this, but one of the papers associated with the survey is mapping out the carbon monoxide formation. Where carbon is in a 1A explosion is a real decider on the explosion mechanism. And carbon is a hard thing to find. It could have been locked up in carbon monoxide formation. So it would be, Webb is really the only way to be able to map that out.
And it might help with figuring out what the progenitors are.
Yeah. There are people in this room who are much smarter. Where's Jared? You back there? Yeah. He wrote was it thesis work and or others? Yeah. The location, the velocity of the carbon, unburnt carbon, is a strong discriminant of proposed explosion mechanisms and progenitor systems for 1As.
Our simulators, and I'm glad we're on this image. So do you have any thoughts that you would translate to our simulator folks? For example, like, is ray-by-ray tracing enough, or, do we need to increase the grid resolution, or
I understand that this talk is being streamed, so I'm going to say no comment, and we can talk about that afterwards.
Fair.
If anybody's been in a room with simulations experts, they're always talking about what is proper and what isn't. But I think, and they're the experts. They would have the most informed decisions. But I think this certainly enough. I mean, Tomas Janka looked at the map in relation here and really had some ideas about what would form the Webb-like network. Okay, there's some processes that would be a signature of.
Great. Let me ask one final question here. Since you're highlighting the filling factor there, and you talked about comparing observations to theory, what are some quantitative things that the theories of explosions should predict? Can they come anywhere close to predicting a filling factor?
Well, I wish you hadn't asked that, John. Because the filling factor we come up with the paper is actually around like, I think 20% or something, and that's something that people have already kind of been using, estimated from what other object? 87A, for instance, right? But one thing is the filling factor, another is the distribution. You know, that's a global average, you know, is it localized, et cetera. I think those are vital contributions. As far as, you know, quantitative numbers, this filling factor, how it's distributed, how it's related to opacity is important for people who are modeling extragalactic supernovae. So they have a light curve, and they make assumptions about these things to trace back, to make an estimate of the ejecta mass. So if you have a filling factor of, in this case, 20%, which is kind of standard, but how it's distributed, what the density contrast is within the ejecta, that can really shape how easily those photons get out. And it could be the case that we're thinking that ejecta are much lighter when they're actually much more massive in these extragalactic explosions.
Great. Okay, let's thank Dan once again.
Thank
for
you
great
again.
talk.
I'll use that one next time. Fred, how are you?
Hi.